Okay. Anyway, I'm going to talk about the near wall awake measurements. The people that will be involved with it: Race Martin will be a new graduate student. Jian Gao is a postdoc in my group. Race Martin will be involved in all LCC measurements, etc. Jian will be more involved with experiments in Hopkins and assembly of the facility, etc. We want to characterize how I don't really need to repeat all the objectives of the projects because they're basically consistent with what Dave has just shown. I just want to mention the separated flow around Prolet spheroid is very different once you go from incidence angles for about 5 degrees to about 20 degrees. At about 5 degrees, you have what we call close separation. When you're at higher angles, you have what we call open separation. This is actually classical visualizations that were performed about 500 years ago, about 30 years ago. So you can see that the close separation, in all cases, by the way, this is not a 6-to-1 Prolet spheroid, but it highlights what happens when you have close separation. You have clearly defined separated flow. There is no flow going across it, and you have a separated bubble. In this particular case, the separated bubble extends all the way to the trailing edge of the model, but it doesn't have to be. And you can see the surface flow visualization of the separated region. So you clearly have zero shear stress line. When you have open separation, if you're going to take the Prolet spheroid at about 20 degrees, at least based on the measurements performed up to now, there is no enclosed separation bubble. The flow near the leading edge of the model actually goes and is not separated at all, and the flow along the front edge, the forward side of the model. So you're going to end up with two stream surfaces actually meet each other, so it's like a fin of a fish if you want. So there is no really an enclosed separation bubble. And this is what really happens here if you look at the perpendicular view of this open separation, you're going to see the familiar pair of counter-rotating vortices that kind of dominates the near wake. So there is no separation. And this type of flow is really a major challenge. Where do you place tripwires? Because look at the orientation of the flow. You see the stream surfaces. They have, it's a very complex system. But anyway, by the way, everything I'm showing you here right now is what occurs at low Reynolds number flows. I don't think we have the slightest idea what we're going to see at high Reynolds numbers. So, but this is kind of, if you want, the basic flow features that we are supposed to investigate. And in relationship to what Dave mentioned before, we tried, and I'll show you the setup, we tried to get the PIV system as close as possible to the leading edge because we really want to see the boundary layer just as the two stream surfaces meet each other. And that will affect the place where the flow detaches from the surface. This domain, I mean, if I can annotate, this domain is really the nightmare to deal and model, and will be sensitive to Reynolds number effects, and Rand's modeling of this is going to be quite a challenge. What really happens here, because you have two stream surfaces that meet each other. And anyway, that will be fun to investigate. I don't have the slightest idea where it would occur at high Reynolds numbers. So this is why I wanted to try to develop a system that will allow us to move the PIV system as close as possible to the leading edge of the model. Anyway, my machine just froze. My machine, just a second. You know what? Oops, here. Here we go. Anyway, so I started working on different concepts of how to actually perform the PIV measurements, at least at this stage, conceptually start accumulating the equipment. I will go, first of all, I will show you here, I mean, kind of basic idea, we can record data with light sheets that are aligned with the axis of the model. This is easier to do. Light sheets that are, and this is, I'm talking about flows that are located very close to the surface. The idea is to resolve the boundary layer in sufficient detail so that we get the shear stresses from the near wall velocity gradients. So this is surfaces lying in the streamwise direction. You have perpendicular surfaces. Those are going to be harder to measure because of the model curvature. Now and then, so these measurements will be performed using internal optics. This means that the illumination and the cameras and the data acquisition system will actually sit inside the model, and the light, I will show you a little more details in a minute. And in the meanwhile, and we're also going to perform measurements that will characterize the near wake. So we're going to have a series of light sheets that are perpendicular to the free stream, and then there's going to be a pair of cameras that will be mounted somewhere along the sting of the model and the sting, and we look actually, so these are all going to be stereo POV measurements, and they will look at the model, look upstream, and then look at light sheets that are aligned perpendicular to the free stream. Right now, at least, I started thinking more carefully about these light sheets because they are more feasible. In terms of arrangements, for whatever reason, I don't know why my computer is doing whatever it feels like.
Okay, you got about 2 minutes.
Huh?
2 minutes.
You know what? Here. So here are the proposed setups. So you have a pair of cameras. This is in this particular streamwise light sheet. You see the pair of cameras line on both sides. It's compact. I can fit all of this to within 16 centimeter width, or everything you see here. If we actually use high resolution cameras, but they are still cameras. So we're actually going to get time average data. So this is the stereo POV system. It will sit on a motorized stage. If the model rotates, if the entire model rotates, then we don't need to rotate it, but all of this will sit on the traversing stage that will enable us to record data in planes that are located in different axial locations. Now, in terms of illumination, the laser will sit outside. The light will be fed into the models via an optical fiber and illuminate the test section. Data, by the way, will be multiplexed to an optical fiber. There are going to be lots and lots of channels of data and redundancy also. So, Dave, if you want to feed data through pressure transducers, etc., there is plenty of channels to feed data. It's all GigE Ethernet, and we have 8 channels of GigE 10 Ethernet, GigE 10 Ethernet signals. So as a result of it, we are not going to have any problem feeding as much data as we want. All of this will go to a data acquisition system located outside. I just want to mention that in parallel, I just want to say that in our water tunnel, we are going to actually create a flow domain with a pressure field that simulates the near field of a model like this, and we're going to install tripwires, and we're going to perform high resolution measurements of the flow upstream at and downstream of the tripwires in order to resolve it. This is going to be in a new refractive index water tunnel. So we're going to create the proper pressure gradients that will simulate the front of the model at a certain selected angle. Now we are going to use either tomographic PIV or holographic PIV depending on application, but the idea is to fully resolve the 3D flow. Right now in the water tunnel, we have no problem measuring even the entire flow round trip. This is, by the way, just a flow around a cube, and the entire cube size is 1 millimeter. We can fully resolve it. So it's in a water tunnel, it's not a problem, and we will do that, and we will follow the evolution of the wake of the trips in order to try to figure out how far, for example, from the trip you have to be located, Otherwise, the local signature of the trip will dominate the separation point, etc., etc. There are a series of objectives, and I've exceeded my time, so that's that.